Perceptron. So what are neural networks? There are algorithms that are inspired by the human brain, and the target is to learn the complex relationships in your data using nodes called neurons. And these connected nodes, the neurons, they model the neurons in the human brain. So neural networks are adapted from the human brain, the connection in the human brain. How different neurons in the human brain are connected. So we use the idea of the human brain and develop the neural networks. And the key advantage is that they're able to learn the nonlinear and complex relationships in the data. Some of the applications that can be, in general, can be applied these to machine learning algorithms are classification problems and prediction problems. And what about AI? So Tesla, the new, the not so new, but the Tesla car that they have introduced. So in the full build of autopilot neural network, it requires 48 networks that work and that take the 70,000 GPU hours to train. You can get this information and visit the link at Tesla and get the information. So one of the recent applications, famous application of neural networks is an autopilot neural network that was used by Tesla. So we have already studied logistic regression. So let's have a brief revisit of the concept of logistic regression. Where logistic regression, what we studied in the previous lecture 3 ABC, we used it for binary classification, yes and no. We studied why I was in 0 and 1. And we defined a linear classifier, a classifier which distinguishes the boundary between two classes. We studied the red dots and the blue dots example, how we can set the boundary between the red and blue dots, and we defined the logistic regression using that. So we defined two models, two classifiers. The first classifier that we used was a hard classifier, and then what we used was a soft classifier. So what was the hard classifier? It is either 1 or 0. The classifier defines the classification into either 1 or 0 if your function f of x is greater than or equal to 0, and it is 0 otherwise. So it defined the classification into two classes. When your f of x is greater than 0, then we say it is one, otherwise it is, for example, it is red, it is 1, otherwise it is blue. So the point here, we say it is blue, and here when we say it, the value of function is greater than 0, then we say it is a 1. So that was your hard classifier. Then we said that this cannot be practically possible because at this point the derivative is not defined, and you know that model updates or weight updates depend on your gradient, and gradient is basically your update with respect to your the partial of your loss function with respect to weight values. So the other one was the soft classifier, softer version. that was defined as h of x 1 plus exponent minus f of x. And if we want to show this linearly, we say that if this is a function f of x, then it is not a hard boundary. We have a slight slope. So your function can be defined at this point, and this is a better option than your hard classifier. So if h of x is close to 1, then we say x is more likely to be in class 1 or red. And if your h of x is close to 0, x more seems like it is a blue. So we can use this version of classifier. So first we came up with the hard classifier in logistic regression, and then we came up with the soft classifier in your logistic regression. And we also know why we have to define the soft classifier, because we want to have the derivative at all points of the function values. So now let's extend this idea. What about here we have binary classification, either 0 or 1. Yi is in 0 or 1. What about multiple classes? So we studied or I addressed that we can have the multiple logistic regression for that. What about the multiple classes? And what about if you don't have a linear boundary? You cannot define, or you want to define, a non-linear boundary. So how we can address that? The relationship becomes more complex and non-linear within your data. So that is our target. So for that, we extend the basic concept of logistic regression. So initially, we are aware that for a linear boundary, your function f of x at this point, for example, we say it is 0. So this is your definition. You can have, for example, 0.5. If h of x is greater than equal to 0.5, you can label x as 1. But if it is less than 0.5, you can label that as 0, where your h of x classifier is defined as a soft boundary. So you can define your logistic regression in this way also. Not exactly 1 and 0. It can be greater than 0.5, and if it is less than 0.5, we say it is 0 for a binary classification problem. Let's look at the example that we studied more closely. So we defined here, if you revisit, basically S is your f of x, right? And you are familiar with wi xij, where j is 0 to n. We defined this. So what we were doing was, we were just summing up w1 x0, w1 x1, w2 x2, wn xn. So this is what we are actually doing, and we are just summing that up. So this is the first part, and the next part was now we are going to, now we are going to redefine f of x as S, because you are now moving into more complex presentation. So that's why we replace your f of x with s. And then what you did was, here you had your f of x, it is replaced, and then y will be your nonlinear transformation of your s. And we have f of x defined like this. What about if we present it graphically? You care? So x1 multiplied by w1, okay, and then x2 multiplied by w2, right, x3 multiplied by w3, or xd multiplied by wd, and we define x naught equals to 1, right? So 1 multiplied by w naught, and then this is your first part, your summation. And then when you have the summation, the next step is to pass the summation to your function f to get your y. So this is the graphical representation. Remember this graph, and here I will repeat it again. First part, the multiplication for all the inputs. X is your predictor variable. We studied that. So now we will call our x i's as input and y I as output. First part is summation part. Multiply each input by the weight w on these links. Now they are called links. And then sum them up. Once you are done, you will have one single value. Then you pass it through a function. That will be your classifier. For example, we have a classifier. You will have a value of f of x. Then you have here s value. Then you pass it through this and then check the value of h of x. What is the value of h of x? If it is greater than 0.5, you say it is 1 in your binary classification. If your h of x is less than 0.5, you say it is 0. So that is the main idea of graphical representation of your logistic regression. 2 steps representation. Now let's move forward. We call this logistic regression or this representation as a perceptron. And we can also call this an artificial neuron because it mimics the function of neurons in the human brain. So this part, this is a neuron. This part is the input of the neuron. This is the output of your neuron. These are the links of your neurons. And each link has weight. And each link will have an input. Okay? And your neuron will have 2 subparts, the summation part, and then get one value and put it in your function, and your function can be a classifier. So logistic regression, we can say, is using just one perceptron. What if we combine multiple perceptron like these? So this is the description or graphical presentation of your perceptron or your one node logistic regression. So one perceptron is your, with only one node is a perceptron, and you can say your logistic regression is just one perceptron. Now let's see if we combine multiple perceptrons, multiple nodes. Weighted summation of your inputs, then nonlinear function. So here we can say this is your function. Multiply your inputs with the weights, sum them up, pass them through the function. If this is a hard limit function, if after you pass it through your f of s, your value is greater than 0, then you assign it a 1. If it is less, then if it is any other value, you assign it a 0. So what we can also represent it in this format. What the perceptron is actually doing. For example, a simpler representation, if we only have two variables, x1 and your x2, it is defined like this. So if an input is above the line, your output is 1, else your output is 0. So I gave you an assignment to find the weight values for a given loss function. So if you have done that assignment, you will really understand what this line means. So this perceptron can basically be represented in the form of a linear boundary. So that W0 plus x1 x2 plus W1 x1 is represented by this linear boundary. So it is, if it is above the line, output is 1. If it is below the line, it is 0. What about defining and